All right, so let's talk about section 5.2. In this section, we want to talk about the addition rule and complements. So the first thing we need to talk about before we get into the addition rule is what it means for events to be disjoint, i.e. mutually exclusive. It means the same thing. It means they have nothing in common, so there's no overlap. So this is an example of a Venn diagram. These would be events A and B are mutually exclusive because they have no items in common, no outcomes in common. And over here you have events that are not mutually exclusive. They have an overlap, if you will. They have an intersection. All right, so our job is to determine whether the following events are disjoint or not disjoint. So you roll a six-sided die, rolling a 4 or rolling a 6. Well, obviously those are disjoint. You can't roll a die and have it turn up both 4 and 6 at the same time. It's either going to be a 4 or it's going to be a 6. Okay, why is the next one not disjoint? Let's see. You roll a six-sided die. You're only going to roll it once. Event A is you roll a 2. Event B is you roll an even number. Okay, well, they have something in common, right? Because 2 is an even number, so therefore 2 is in the overlap. If you will, if you were going to do a diagram of that one, the even numbers would be over here, 2, 4, and 6. 2 would be in this little overlap. 4 and 6 would be over here, and there's nothing in this blue half moon at all, right? It's just 2 and then 4 and 6. But nevertheless, there's still an intersection there, right? Okay. So what about decks of cards? So you're going to draw a single card. Event A is you drew a queen. Event B is you drew a 9. Well, your card is either one or the other. You can't be both, right? So that's disjoint, right? AKA mutually exclusive. So I could say that. Mutually exclusive. Right? Meaning, what that means is that once you have one, you cannot have the other. It excludes the other. See? So that's what it means to be mutually exclusive. And these ones would be not mutually exclusive. If I could write it. There we go. All right, what about the next one? You draw a queen, that's one event, and you draw a heart, that's the other event. Okay, well, there's such a thing as the Queen of Hearts, right? So, if you think about in this diagram again, over here would be all the queens, right? So Queen of Spades, Queen of Diamonds, Queen of Hearts, Queen of Clubs. Over here is all the hearts, Ace, 2, 3, 4, 5, 6, 7, right? So the overlap is the Queen of Hearts. So the other 3 queens are sitting over here in the blue region. The Queen of Hearts is right in there in the purple region. And then over here in the pinkish is all the other hearts, right, that are not the queen. The king, the jack, the 10, they're all over here, right? So that would be not mutually exclusive. They have an overlap. If they have an overlap, that is not disjoint, right? In fact, I'll make a note of that. They have overlap. It's also called an intersection, right? There is something that they have in common, right? It is possible to draw both of those things at the same time. Same thing with up here, right? It's possible to roll a 2 and an even number at the same time, right? Okay, now why is that important? Well, because if events are disjoint, it changes how we treat them. So we're going to learn the addition rule for disjoint events, which is pretty simple. We've actually kind of used it already because it's so easy that people kind of use it without really thinking about it. So I have here the following table showing the number of graduates from Jackson Community College for the spring 2010 to winter 2011 by degree. We already found these probabilities. They should be sitting, if I'm not mistaken, right here in our Excel spreadsheet. Okay, so there they are. Ta-da! So what is the probability that a randomly selected JCC graduate obtains an associate's degree of any kind? Okay, well, there's Associate of Arts. Hold on. Better write this down. So you could get Associate of Arts, or what are the other options? Hold on, let me make this smaller so I can see here. There we go. Or the AAS, or that's Associate in Applied Science. There's an Associate in General Studies, or, oops. Then the last one is Associates in Science. So AS. Oopsie. There we go. Okay, so then what you do is you add up the probabilities of each one of those. So Associate in Arts is 0.0613. Associate in Applied Science, Associate in General Studies, and Associate in Science. You assume that they're disjoint. because, you know, if you're getting 1 degree, you're assuming you're not getting the other. And now I know that's technically, it is possible to get 2 degrees at the same time, but we're just going to assume that that was not the case. All right, there we go. Then you add them all up and you get 0.6482. All right, now what about down here? Oh, contingency table. So I took the numbers from 2011. This is different. So this is the 2011 fall enrollments. These are the certificate and degree types, right, for different genders based on the fall enrollments. So we're going to need to find the marginal frequency. So I'm going to have to take this over to, oh, there it is. I've already put it in there. Okay, we're going to have to find the totals here. So remember, that's the sum of all of these, that first row, and then I'll just drag it down. And then I'll do the same over here, equals sum of these two. I'm just going to drag it across. There we go. And again, if you don't have, you won't have words, so you might have to type that in yourself, but it's all right. Oops. There we go. Got my numbers now. All right, so there's the, now remember that was called the marginal frequency. We learned how to do that in section 4.4. Now the column variable is the degree type, right? Associate in arts, associate in applied science, and so on. Then we have the 2 genders, right? That's the row variable. The cell for associate in general studies and female, okay, that was AGS, that's associate in general studies, and female, that'd be this cell right here, right? So that's the 196. All right, find the probability that a randomly selected JCC graduate earned an AGS or an AS. Okay, so there's 385 out of 6548 total for AGS. And then there's 622. I realize I should have written a little bit more here. So what I want is the probability of AGS or, and then what was the other one? Associate in science. There we go. And so then what I do is I find this probability of AGS and I add to it the probability of AS. There we go, that's better. And that's equal to 385, this guy right here, divided by the total, plus this one right here. Oops, don't do that. This one right here divided by the total. All right, I'll highlight those 2 cells so you can see them better. These 2. Right there. Okay. Now, how do I get the decimal? Well, I mean, you can just do it anywhere you want. You can say, okay, equals the sum of these 2, and then the probability would be equal to that 1007 divided by that number 6548. So there you go. I just happen to know it was 1538. Because I worked it ahead of time, but that's how you could get Excel to work it for you. All right, we're done with that one. So we've done a contingency table and we've done a probability distribution. So next is going to come the old, hey, you build it yourself and hope for the best, the classical stuff. So suppose you're going to toss 2 fair 6-sided dice and note the side that faces up on both dice. So how large is that sample space? Well, remember, we already learned that in 5.1. You take 6 times 6, because there's 6 sides to each die, and you multiply it and you get 36. So why would we not want to make a tree diagram for this? Well, it's because there'd be so many branches it'd be hard to fit on a page, right? I mean, the tree diagram stuff we learned in 5.1 is great for small sample spaces. It kind of helps organize your thoughts. But for big sample spaces, it's just kind of cumbersome. Okay. All right, so construct the sample space, and I did right here. So you could roll a 1 on the first die and a 1 on the second. You could roll a 1 on the first die and a 2 on the second, 1 on the first die and 3 on the second, and so on. Then you go again, 2 on the first die, 1, 2 on the first die, 2, 3, 2, 4, and so on. And you'll have all 36 by the time it's over. And it helps with something like this to put it in a nice table, kind of keep your ducks in a row, literally and figuratively, right? Tree diagram you could do, it'd just be really hard, right? I wouldn't want to fit it on a piece of paper. All right, so what is the assumed probability for each outcome? Well, you assume the dice are fair, right? So if the dice are fair and each toss is equally likely, there's 36 outcomes, so each one has a 1 out of 36 chance, right? Of course, right? I know I'm right. All right, so with that, we will move on to the next bit and say, okay, if that's the case, in a lot of games, they don't want to know what the two dice were separately. They want you to add them up. You want the sum of two dice is what really matters. Like Monopoly is one of those games. So construct a sampling distribution, construct a probability distribution for the sum of two fair six-sided dice are right. Not a sampling distribution, that's something else. All right, so, well, you could have your dice add up to 2, right? 1 and 1 makes 2. You could add up to 3. 1 and 2 makes 3, and 2 and 1 makes 3, right? This one and this one, right? Or you could add up to 4. 3 and 1, 2 and 2, 1 and 3, and so on. Okay, so you can work your way along the diagonals of that table you've made before, and you'll come up with these probabilities right here. Now, the highest probability you can ever have is 7. 7 comes across the diagonal. So 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, right? So that's the most likely. And then you start working your way back down as you keep moving down the table. And eventually you end up at 1 out of 36 again for 12. So there. I don't know what I just did there. All right, so are these probabilities classical or empirical? Oh, they're classical, right? We didn't roll any dice, right, and clock the results or record the results, right? We just set up a hypothetical sample space, right, and worked from there. All right, what's the probability that the dice will add up to 7 or 11, which is an automatic win if you roll it first in craps, if you play at the casino. So that's 7 or 11, so that I need the probability of 7, which is 6 out of 36, plus the probability of 11, which is 2 out of 36. That makes a total of 8 out of 36, which is a decimal of 0.2 repeating. All right, what about rolling snake eyes? If you roll snake eyes, which is 2 1s, that's an automatic loss, and the chances of that is 1 out of 36. Okay. Which it's occurring to me that this is not right. It's 0.0277. There we go. All right, looking back at the example we had to start the unit, way back here, first page, it said, you know, are there better chances of rolling boxcars or randomly drawing an ace out of a deck of cards? Okay. So boxcars would be, not that far. There we go. So boxcars, let's see here. There we go. All right, boxcars is a sum of 12. And the probability of a sum of 12 is 1 out of 36, which works out to 0.027777 in a decimal. Now the probability of an ace is 4 out of 52, because there's 4 aces in a deck out of 52 cards, which is 0.077. So since this has a higher probability, the probability of drawing an ace is higher, therefore drawing an ace is more likely than rolling boxcars because it has a higher probability. All right, we're all done with that. I will meet you back here for the general addition rule, which is how to deal with things when they're not disjoint. See you then.